Let me see. Okay, I have 15 minutes to revisit our Leslie matrix model. That's interesting thing. It took me a couple of hours to figure out all those details. Back to the one particular example. That bird has a maximum 3 years of span, so we are talking about an age-structured model. And during the first year, the bird does not breed. And you may remember, the female in the second year lays 10 eggs. And in the third year, lay 8 eggs. And we assume only 15% of the first age survive to the second year, and the half from the second year survive to the third year. So in order to make it easier, we only think about the female, and then of course we assume among the 10 eggs, 5 are female eggs, among the 8 eggs, 4 are female. Well, you might still remember this diagram, the state machine. And that's the H1, H2, H3. Well, actually, this is not a complete model. Look, we said in the H1 only 15% to the H2. What about the other 85% of the population? They died, right? That is not captured. Death is not complete. As a flow, this is not completed. And for the second year, 50 survived to the third year. How about another 50%? Died. We need to capture that, but it's not here. And as reborn, the second year population have 5 eggs, go back into the first year, and then the third year have 4 eggs, go back to the first year. That's good. And then how about the third year population? 100% all died, right? After the third year, they only live for 3 years. So this state transition is not completed with this flow here. Look at the only transition, only for survivors, but not for the death. The whole point is once the year advances, 100% need to be out. So that's the little difference when you use a stellar model. And you might still remember this matrix, we call it the Leslie matrix. It captures the relationship the first year equals 5 times the population of the second year in last time. The next year, the second year population equals only 0.515 of the first year population in the previous year. And the new population of the third year equals half of the population of the previous second year. So you remember that, I hope. But how about I like a differential equation? You see my previous model, they all used the differential equation, the Marshall model, and the carrying capacity model, computation model. We all use differential equation. Then you ask, can I use the differential equation model to think about the Leslie matrix? The answer is yes. Depends on how big a population you have. If you have a huge population, you consider hundreds of years, sure, you get a decent result. Your result may be exactly like what you did in the first module. So that's what we do. And all you need to remember is the derivative, by definition, equals this, goes to 0, p right now, p a moment ago, or you can put the at if you want, divided by dt. So you can do this way too. Then you do the minus. Well, if you let the dt be 1, oh, you say you want the dt go to 0, how can you let it be 1? Depends. 1, you can talk about a 1 millisecond, 1 nanosecond, 1 minute, 1 half year, or 1 year. Depends how long along your timeline. If I consider a million years, then 1 year is nothing. It's like 1 millionth of the tick. If I only consider 1 second, and the 1 millisecond is still too long. So it's really relative. Depends on the scale. That's why we talk about scaling. So if you look at this way, agree with me, dt equal 1 is not too bad. We are going to consider hundreds of years. Or then, look, this change divided by the dt, which equal 1, you can approximate think as a derivative of the 3 functions to t. And if we agree these 3 functions are the derivatives, and then that's the new one. The new one can represent as this Lesson matrix, and the old one is this itself. And if you factor out this x1, x2, x3, and what you get is this matrix. See, you minus, and then use the Lesson matrix minus itself. That's when you get the -1. Let me do a little calculation. Maybe extend a little bit. You factor out x1, x2, x3, and then you get the Lesson matrix 0, 5, 4, 0.15, 0, 0, 0.5, 0. And the minus what? When you take it out, you need to minus the identity 1, 0, 0, 0, 1, 0, 0, 0, 1. When you subtract, then that's how you get the -1 here, -1 here, -1 here. So now you get a different representation. Let me erase this ugly thing. And your representation is a differential equation. Look, the derivative of the time equals this matrix. That's not the Lesson matrix, but the Lesson matrix minus I here. And then you times the population. What is minus I? Means you minus the population itself after 1 year. And the second year you minus it itself. Well, go back to here. What means -1? See, these are the -1. You add all together, it's 100%. After 1 year, all the first year no longer exist. Either survived but changed into the second year or died. Same thing about the second year. After the tick of the new year, for the new breeding season, all the population in the second year either become the third year population or all died. That's -1. Or the same for the third year, so what? After the next year, all died. So that's what you mean in here, in your equation, -1. That means the change of x1 equals all out. And then you add the increase. So this means all the old population died. 5 from the second population X, 4X from the third year breeder. That's how you read it. So you look at the change instead of the population itself.